Hey, Nicholas is with us.
Good morning.
Good morning. Well, let's see, I need to adjust that somehow. I guess that's okay. There we go. Well, let's see who we got with us this morning. We have, oh my, we have Taylor, Ashley, Braxton, Jesus, Mark, uh, Nicholas, Stuart, Nicholas, Mark, Jesus, Braxton. We got a good class. Did any of you have a comment or question? Hey, we've got 1 minute before class. Here's your chance. Do you have a comment or question? I guess not. Well, we're going to study collisions again. We've been studying them. Maybe we should go over some of the basics. You're supposed to do a take-home test for me. It's due Friday. No. It's due Saturday. It's due Saturday. It's available to you now. It's over chapters 13, 14, and 15. Maybe I should write that on the board. I don't know if there's any actual homework that I've assigned. I guess I just let you study for your test. Huh? The exam is available now on chapter 13, 14, 15, and it's due Saturday. Today's Wednesday. And I don't guess there's any homework. Okay. All right, good. Well, let's do some homework problems. That sounds like fun. I was going to give you a 5-minute talk on the basics here. I think I've told you this before, but let me tell it to you again. If you have a system of particles, and you add up the impulses on all the particles, that's going to give you the sum of the changes in their momenta. This is called the impulse momentum equation. This thing here is called impulse. And these things are called momenta. Momenta is plural, momentum is singular. And there's a very special case. If you have two bodies that crash into each other, the forces between the two bodies, here, I'll draw a picture here. here's two cue balls. I bet you guys play pool. Here they come, these cue. Well, one's a cue ball and one's maybe an 8-ball, okay? This is the 8-ball. And then see when they hit, the forces are equal and opposite. This ball puts a force on the, let's say that's number 3. I think that's green, isn't it? You guys that spend a lot of time playing pool, I think that number 3 is green from my memory. See, I remember when I should have been studying, I was down at the pool hall playing pool. Now the 8-ball, it's black, if I remember. Let me check with my students here. How about it, Braxton? Unmute and say hello, Braxton.
Hello.
Hey, Braxton, did I get the colors right? Is it the 3-ball green and the cue ball black?
I know the 8-ball's black. The green ball, I think it's 3. I'm not sure. It's been a while since I played pool.
Good for you, Braxton. You've been studying and doing your homework instead of goofing off playing pool. Proud of you. However, it does kind of relieve tension to go down there and play pool. But here's the point. When they hit, that 8-ball puts a force on the 3-ball, and the 3-ball puts a force on the 8-ball. They're equal and opposite, and the collision happens real fast. It's just a click, just a sharp click. It's a tiny fraction of a second. And so when you total up the impulses, you get 0 in a collision between 2 balls. So if that's 0, what that means is the sum of the momenta is 0. Because if the left-hand side here is 0, and you got an equal sign, well, then this here is 0. Now what this is, that's the change in momentum. We'll label that 3. You have the mass of the 3-ball times the final velocity of the 3-ball minus the mass of the 3-ball times the initial velocity of the 3-ball. See, that's the change in momentum of the 3-ball. Now the change in momentum of the 8-ball is the mass of the 8-ball times the final velocity of the 8-ball minus the mass of the 8-ball times the initial velocity of the 8-ball. And all of that is going to equal 0 because the left-hand side of this equation is 0. Then if you sort these terms out and put the initial values on one side, I think I've done this before, but sometimes it's good to go over important things. I think this one's important. This is called the conservation of linear momentum. See, this is the total initial momentum. Now, this is going to be the final momentum. I did a little algebra there. I took this equation here and I did a little algebra. Can you follow that okay? I bet you can. I bet, wait a minute. Did I do that right? Yeah. Yeah, I think I did that right. Yeah. double check me now, make sure I got that right. Yeah. Now
The,
they have,
the,
yeah, go ahead.
the three ball's actually red.
Oh, the three. Well, which one's green?
I think that's the 4. But I don't think it'll affect the answer, so I think it's fine.
It doesn't matter, does it? But
No,
I'm going now. Who am I talking to?
this is Taylor.
We're going to give Taylor a red thank you point there. And the 3 ball, Taylor tells me, is red. Is it the 2 ball that's yellow? The 2 ball is yellow, isn't it?
That's the 1 ball.
Oh, is that the 1 ball? Can you
That's
tell
the
it's
first
been
one you
a
hit.
while? It's been a while.
Maybe a
since
little
I
while.
played. Yeah. Okay, now this here, you could write this as the sum of the initial momenta, and you could write all of this as the sum of the final momenta. And this equation here has a name. It's called the conservation. Is there room for me? Yeah, there's room here. The conservation of momentum. It's a biggie. It is a real big deal. Conservation of momentum. Well, there you go. I've given you a little bit of review there, and we figured out the 3 ball is red. And which one did you say was green? 4?
I think it's the 4. I'm not sure which one's green.
Well, we'll notice next time we go. We'll figure it out eventually. Okay, well let's. I'm going to erase all this, and we're going to work some problems, and we're going to use this conservation of momentum. But now wait a minute. Let me show you that other equation. I've shown you this, but repetition is good. It won't hurt us to write this equation. Now, this equation is called the coefficient of restitution. Well, there's a coefficient of restitution, and the symbol the book uses, I think they use a little lowercase epsilon. Is that right? Just a minute. Let me dig in my book here. And I'm going to look it up. This is chapter 15. And they've got, yep. Well, they actually, no, they don't use the Greek letter epsilon. They just, I'm wrong. They just use a lowercase, good old English lowercase e. And this equation goes like this. If I can remember it right. I don't want to lie to you, so let me double check that. Yeah, that's right. I think they use 2 instead of final and 1 instead of I for initial, but it's the same thing. And that equation's on page 267. This equation is called the coefficient of restitution equation. And this little guy right here, this little e, that is the coefficient of restitution. Now, the definition of E is the impulse of restitution No. It's the impulse of deformation divided by the impulse of restitution. That's the definition of it. Do they tell you that? Yeah, there it is. That's also on page 267. See, in a collision, you have deformation, like when that pickup truck rear-ended me, he came and hit my rear bumper and smashed my rear bumper, just kind of messed up the back of my car. That was the deformation part. But then he kind of bounced back, and I took off. He made me just scoot like crazy. I went from 20 miles an hour to about 40 miles an hour in a hurry. And that's the restitution. What happens is the bumper, it doesn't go back the way it was, but it kind of springs back a little bit. It's sort of like you take a rubber ball and you squeeze it, you got deformation. Well, when you let go of the rubber ball, it bounces back. Now, car bumpers don't bounce back like rubber balls, but they do have some restitution. And do I have that right? No, I've got it backwards. Let me make it right. Somebody could have gotten a thank you point because I had it upside down. It's the force, the numerator is the force of restitution, and the denominator is the force of deformation. It turns out that, well, this is force, but this is impulse when you have integrate it with time. It turns out the impulse of restitution is smaller, unless you have a perfect collision. Now, if you have a perfect collision, these are equal, and coefficient of restitution is 1. Here, let me tell you that, and then we'll work some problems. There's some room over here. This will work. If E is equal to 1, then you have a perfectly elastic it's a perfectly elastic collision. They have these super balls that really bounce good. If you have a super ball and you drop it, it bounces and it comes back darn near to the same height that you dropped it. But not quite. Even the super ball won't come back exactly to the same place where you dropped it, because it loses a little bit of its energy in the collision. Now, if E is less than 1, then you've got a normal, everyday, it's an inelastic collision. I think that's what they call it in the book. It's an inelastic collision. I call it a real world collision. It's like with my when my car was rear-ended by that pickup truck. That was the real world. Now, if E is 0, what that is, you get yourself a ball of mud. Go out in the backyard and get some dirt and make it wet and make yourself a ball of mud and drop it on the sidewalk. Splat. It doesn't bounce. That ball of mud, it hits the pavement there and that's it. Splat. It doesn't bounce. And it has a coefficient of restitution of 0. There is no restitution. That ball of mud hits the pavement and stops. Well, it kind of flattens out, but it doesn't bounce. So there's the three things that can happen. These you study in Physics 1. And I know you guys have all taken Physics 1, but see, they didn't teach you about this one here. And really, that's more important because that's what happens out there in the real world. Well, there's your review. Now we're going to work some problems. Is there any questions? Do you have any questions? Okay, well, let's do some problems then. This one here is 15. Let's do 1547. That looks like fun. We're going to do problem 1547. And unless you speak up mighty fast, because I'm going to erase all this stuff. All right. Okay, this is problem 1547. Let me find it. 1547. I found it. It's on page 264. You got two freight cars. Well, one of them's more of an oil tanker. One of them's a boxcar. 30 megagram freight car. Okay, well, here I'll draw them. We have a 30 megagram. I don't want megagrams. I want 30,000. Would it be 30,000 kilograms? I think so. It's 30 megagrams. So what that is 30,000 kilograms. And then you have a 15 megagram freight car here. This is more of a, no, it's more of a tank car. I don't know what it's got in it, maybe oil. And it's 15 megagrams, in other words, 15,000 kilograms. When they uncouple these cars and they put them on a siding, have you ever seen the way they move those cars? They don't have an engine on the siding to move them. They send a person out there with a it's kind of like a crowbar thing. It's a kind of a big, long handled, kind of got a curve on the end, and they put that right under one of the wheels, and I forget whether they push on it or pull on it, but it moves the car about 2 inches, and then they have to scoot it under there again, and they can move that car 10 feet. Takes a little hard work, even though if it's filled with grain or something heavy. Now this one here has a spring. That spring has 3 meganewtons per meter. Again, I don't like the stinking mega, so we're going to go 3,000 kilonewtons per meter. That's your spring constant in Hooke's law. Okay. Now this car here, he's going 20 kilometers per hour. I don't want kilometers per hour, so we're going to convert that. You know what that is? That's 20,000 meters every 3,600 seconds. There's 3,600 seconds in an hour. So that boxcar is going 20,000 divided by 3,600. It's going 5.55, a bunch of fives, meters per second. It's going this way. 5.55, a whole bunch of fives, meters per second. Now let's do this tank car. Now it's going 10 kilometers per hour. Now let's convert that. 10 kilometers per hour. I don't want kilometers. Let's make it 10,000 meters per hour. And an hour is 3,600 seconds. So that's 10,000 divided by 3,600. That's 2.777, a whole bunch of sevens, meters per second. But it's going this way. There's going to be a head-on collision. It's going slower, though. It'll make that arrow a little smaller. 2.777 meters a second. They're going to hit. Then what happens? Find the maximum compression of the spring mounted on the car. Neglect rolling resistance. Okay, well, let's see what we can do. Now I'm going to erase all this stuff here because I think we got that figured out pretty good. I better leave that spring constant, though. To refresh your memory about the spring constant, the force of a spring is equal, well, it's actually negative the spring constant times the deformation of the spring. And now the energy, the potential energy stored in a spring is 1/2 kx squared. Now, if you have your spring that's not relaxed to start with, then you got to do this here. I think we've shown you that, or you can read the book. But in this case here, that spring, before the collision, it doesn't have any deformation. So you don't need a x1 term. It's just like that. I think I integrated this and we got there. So you can integrate it. Energy is equal to the work. Well, it's equal to the negative of the work done. Remember our equation? The change in potential energy. It's really defined to equal negative of the work done. And the work done is the integral of f dx. I won't bore you by doing it again, but if you integrate this from 0 to x, you will get that. If you don't, let me know. Okay, there's a collision between two bodies, and so momentum is conserved. Remember, I just had a little sermonette about that, didn't I? Because see, the forces are equal and opposite when they hit, and the time of the collision is the same for both bodies. So we get to use this wonderful equation here. And this equation has a name. And I'm going to see if anybody is awake out there. Ashley, let me pick on you, Ashley. Unmute and say hello, please.
Hello.
Hi. Ashley, this equation is very, very important to us. and it's got a name. What's the name of that equation, Ashley?
Conservation of linear momentum.
Oh, she's got it. She's awake. She's listening. She knows darn well that that's the conservation of linear momentum. Now later, not much far down the road, we're moving along. Gosh, it's October 14th already. We will study the conservation of angular momentum. And it will look something like this. We don't know how to do that yet. Where this right here is called angular momentum, that's the initial angular momentum, and this is the final angular momentum. But you don't use mass, you use this thing here that we will study. It's called the moment of inertia. And this thing here is called the angular velocity. You've probably heard of both of those, but we don't know anything about that yet, but we're gonna be there pretty soon. Okay, well, let's write our equation. Here we go. Let's see, we got the 30,000 kilograms times 5 point blah, 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 meters a second, plus, see, sigma means add, it means plus 15,000 kilograms times, now watch it though, these are vectors. You see those little vector signs over those? You have to write that as a negative 2.777 because it's going to the left. It's a vector. See, the positive x direction is going to the right, and this one's going to the right, so it's positive. But this one's going to the left, so it's negative, equals, there's your equal sign, equals the 30, oh gee, I'm gonna run out of room, I can see it happening, equals the 30,000 times the velocity, well now, here's where you gotta decide when you're talking about, if you wanna talk about after the collision is over, then what you would write would be, is this body A and body B? Is that what they call it? Let me look and see here. Yeah. This is body A and this is body B. If you want to talk about when the collision is over, then you'd have VA plus, running out of room here, 15,000 VB. But I'm not interested in that because if you read the problem, they want to know something about the maximum compression of the spring. See, that spring is going to compress and then it's going to expand, it's going to bounce back. But when the collision is at its maximum, these two bodies will have the same velocity. I gave you a talk about that last time. When the collision is at its peak and the forces are maximum, the two bodies are going at the same velocity. I don't know if you remember me telling you that. So you don't need two different velocities here. You just need one. But if both bodies are going at that velocity, then the total mass would be 45,000 kilograms times, I don't know what to call it, just call it V there. That would be the velocity at the peak of the collision when the spring is compressed to its maximum. Hey, look, here's an equation with only one unknown. I'm going to give you a minute to solve that. I'm going to solve it. Go ahead. Find the velocity of the two bodies at the peak of the collision when they both have the same velocity. Okay? Go for it. Okay. Let me call on one of my excellent students here. Jackson. Jackson, unmute and say hello, please. Hey, Jackson, did I give you enough time to solve this and get the combined velocity of the two bodies when they're at the peak of the collision?
Yeah, I'm getting positive 2.777.
That's what I got. That's interesting.
Okay.
You know what? This body here comes in at 2.777. But at the peak of the collision, when that spring is compressed the most, it's going that way. In fact, they both are. Now this one slows down. This was 5 point something, and now it's only going 2.77 to the right. But this one, man, it changed direction. It came in at 2.77, and now it's going to the right, 2.777. And now I want to know, I need a couple of uh-huhs from other people. Anybody get the same thing? If so, say uh-huh.
Uh-huh.
Yeah, well, there's one. I need another uh-huh.
Yep.
Yep, that's fine. Okay, well, we made some progress, but that doesn't answer what they wanted. All we know is the two together are going at that speed. Now, here's the plan. We're going to go back to chapter 14 to energy. And we're going to use the conservation of energy. Now, you got to be careful about it. Remember, it only works if there's no outside forces that do work. But in this case here, we're going to neglect any kind of friction. And spring forces are conservative. The only two kinds of forces that give you potential energy are gravity and elastic forces. Gravity doesn't play a role here because they're not going up or down. So we can use conservation of energy. And let me make some room here, and I'm going to write conservation of energy. Now, the way that works is the initial kinetic energy and the initial potential energy, and this would be the elastic potential energy because nobody's going up or down. We don't need to worry about gravitational potential energy, is equal to the final kinetic energy plus the final potential energy. Now, this equation has a name. It's called the conservation of mechanical energy. Here, let me write it. It's the conservation. Your book just says the conservation of energy. But you probably should stick the word mechanical in there because if you want it to always work, you would have to include temperature effects. And this is neglecting those. You would, if you wanted a true conservation of energy equation, they call that the first law of thermodynamics. But we get to use this here because we're neglecting any temperature effects. Okay, well, let's plug in the numbers. Here we go. Now, the initial kinetic energy is 1/2 30,000 kilograms times 5.555 meters per second squared plus. Now, kinetic energy is always plus. I don't care if you're going to the left and the velocity is negative. See, when you square negative, you get a plus. So this one here is going to be 15,000 times 2. Wait a minute, I forgot the half. I just about goofed up there. Kinetic energy is 1/2 the mass, 15,000 times 2.777 squared. There we go. Well, there is no elastic potential energy yet because they haven't collided yet. So that's it for the left-hand side. Now on the right-hand side, we have kinetic energy. We have 1/2 45,000 times 2.777 squared plus your elastic. Oh, I'm running out of space here. This is the spring, the potential energy of your spring, and we'll get that, and then we'll use this equation here. Potential energy of your spring is 1/2 kx squared. But first I want you to plug in this equation here. Let's box it up. I want you to find. There's this nice equation here. I want you to find the elastic potential energy at the maximum compression of the spring. Plug all that stuff in. Go for it. You can do it. Can you read all that? Yeah, I bet you can. All right, solve that. Gee, I get a humongous number. Let me go to one of my excellent students here. Alex, unmute and say hello, please. Earth calling Alex. Earth calling Alex. Come in, Alex. Uh-oh, coffee break. Jackson, unmute and say hello, please.
Hey.
Yeah. Hey,
I got
Jackson. Did you get the? Got lost there. Did you get the potential energy of the spring when it's compressed to its maximum compression. Did you get it?
I think so. I got
What'd you get?
347,194.
That's what I got. Now wait a minute. I got 347,
Mhm.
307. You got 347 something else?
Yeah, 194. Let me check.
Did you round off anything? Oh, I tell you what
No.
the difference is. When I put in these 5s and these 7s, I think I just kept pushing my buttons. You're fine. You're fine. It basically it's 347,000 with a little bit left over. Let's don't fight over that. I think it's a matter of you put in exactly what I wrote, and I think I put in about 6 or 8 5s there. But I'm talking to Jackson now, right? Jackson, what's the units? We got to have units. What are the units? See this?
Be
This stuff.
Newton by meters.
Say that again, Jackson.
Be Newton meters. Or
Yeah, it's Newton meters. That's exactly right. Now, what's another name for a Newton meter, Jackson?
joule.
Yeah, there you go. He knows. It's 347,000 something joules. Good going, Jackson. Okay, now look at here. We know K. Let me circle it. K is 3,000. Here, let me write this out. I need some room, right? I don't need all this stuff. All right, now here's our equation for elastic potential energy. 1/2 3,000 kilonewtons per meter times x squared. Now what this is the compression of the spring is equal to 347. Let me do it like Jackson did it. Just a minute. I'm going to do this again and get the number that Jackson got. Hang on. Jackson, did you get 347,194? Is that what you got?
Yeah.
Let's use Jackson's number because that's what I wrote. And that's what you guys should have had if you plugged in what I said. So we got 347,194 joules. And now we're going to solve for the compression, the maximum compression of that spring. I'm going to be quiet for a minute. I want you to do it. Go for it. Well, I did that, and I got 0.481 meters that the spring is compressed at the height of the collision. Now let's see how we did. Go to the back. This was problem 15. This is problem 1547. And we'll see what the answer book has to say. Oh, gee, somebody wants me on my cell phone. They want money is what they want. Okay, now let's see. 1547, it says here, hang on. Trying to find the answer book back here. 1547. Okay, here's what the answer book says. If you look up the answer in the back, they said 481 millimeters. Hey, that's the same thing. We did great. We got the right answer. Is there any question about problem 1547? Well, okay. I guess you're all right with it. Let's do another one. Before we leave this topic, let me draw you that graph that I drew for you. I just need some room here. See, if you plot force versus time, we're pretending this is a elastic collision. So it starts off at zero force, it builds up quickly to a maximum, and then it comes down back to a zero force. See, right here, that's when the collision is at its peak. That's when the collision is at its peak. And if you wanted to find the force involved between these cars, because of the symmetry, see, this would be the force on car B, and this would be the force on car A. It's equal and opposite at any moment, because the forces are equal and opposite. And if you wanted to find how big that force is, you know it's going to occur at the halfway point, right? Let me think, is that right? Yeah, because it's F equals kx, the force is linear with the deformation. And so if you plugged in the 0.2, what's half of that? Half of 481 is 0.2405. And we know what the K is. The K is 3,000 kilonewtons per meter. You could find what that force is. The maximum force between the boxcar and the tank car. Just for fun, I'll give you 30 seconds. Go ahead, and find what that maximum force would be at the height of the collision. Go ahead. Did you get 721.5 kilonewtons?
Yeah.
Yeah, good going. Well, that's a bunch, but hey, these are big, heavy things. All right, now we're going to do a different problem, if you're happy with that. But I wanted to review. See, that was a case of a perfectly elastic collision. The real world collisions aren't like that. And I showed you, I talked about that the last time. And the way it works is the impulse of deformation is bigger than the impulse of restitution. But see, they're equal. The restitution and the deformation impulses are equal if you have a perfect collision. Okay, let's do 1564. And this one we get to use that, what do they call it? Restitution something or other, the coefficient of restitution equation. So help me find it. I've lost my place again. 1564. Help me find it. I'm snooping around here. Okay. Maybe you can help me here. Yeah, I beat you to it. 1564. Now it's got a star on it, but I looked up the answer in the answer book, so we'll be okay. Yeah, we'll be fine. 1564. It's got a little, well, it's not a star. It's a kind of a snowflake. It's an asterisk. That means they don't have the answer in the back, but I got an answer book. Ball A has a mass of 3 kilograms. Here, let's draw it. Here's A. It's not a pool ball because they don't weigh that much. My guess is they weigh about a half a kilogram, maybe. No way is a pool ball weigh 3 kilograms. This thing's 3 kilograms and it's going 8 meters a second. And the other ball, ball B, it's got a mass of 2 kilograms. It must be made of aluminum maybe, and this is made of steel, something like that, because they look like they're the same size, but it doesn't have the same mass. And it's going 4 meters a second. It's not going as fast. 4 meters a second. Okay. Now they collide. And the coefficient of restitution is 0.7. All right, now we're going to find the velocity after the collision. Okay. Well, you get to use the coefficient or the what do they call conservation of momentum equation. You know, the sum of all the initial momenta is equal to the sum of all the final momenta. That's called the conservation of momentum equation. So let's do it. Let's see, we have 3 kilogram times 8 meters a second plus 2 kilogram times minus 4 meters a second. See, it's minus because it's going the other way. Equals 3, we'll call it VA plus 2 VB. There's our conservation of momentum equation. All right. Well, we can't solve it though, because see, there's 2 unknowns and we only have 1 equation. Ah, but we have another equation. We have this little guy here. And this is, here, let's do it this way. VB minus VA, and this is VA initial. See, these will be final. VA initial is 8 minus VB initial, which is minus 4. They call that the coefficient of restitution equation. Okay. Let's clean these up and write these equations pretty, make them pretty, and then we'll do some algebra here. And there's a little room right here. I might be able to fit it in. 3 times 8 is 24, and 2 times 4 is minus 8. And you know what? I think that makes 16. I think we got 16 equals 3 VA plus 2 VB. I've just cleaned up this equation. Now, if I did that wrong, you let me know. Now, this one here, you got 8 subtract a negative 4. That makes 12, you know what? And this is 0.7. They gave us that. Wasn't that nice? What's 0.7 times 12? Hang on. 12 times 0.7. I'm getting 8.4. So this equation here is 8.4 equals VB minus VA. Now here's our 2 equations in 2 unknowns. And all we got to do is some algebra now. Now what I would do is I would multiply this whole equation by 3. And here's what I would get. 25.2 equals 3VB minus 3VA. I don't need this one anymore. Just forget it. Now, if you add these 2 equations, the 3VA and the minus 3VA go bye-bye, and you get 5VB. So you have 5VB equals, whatever 16 plus 25.2 is. That's too hard for me, but my calculator can do it. I'm getting 41.2. So VB is equal to 8.24 meters per second. And now see, we can get VA. You can plug in any of these 3 equations and get VA. So let me do it. I'm getting VA as a negative 0.16 meters per second. Let me draw that for you. I need some room here to work. Now, let me just get rid of some of this. See, this is the situation before. Before, these are colliding head on. And now I'm going to draw the after. After the collision is over, of course, they're going to be down, I think they're going to be down here to the right a ways. A is actually going to be bouncing back. A is going to have a teeny tiny velocity of 0.16 going the other way. But B is going to have a velocity quite big of 8.24 meters per second. B takes off. I wonder how come B takes off? Well, because it's a smaller mass. See, 3 kilograms is bigger than 2 kilograms. And this thing's coming in 8 meters a second, and it's only going 4 meters a second. It's kind of like you've got a 160-pound right in that's going this way, and you have a 200-something pound tackle, I guess, that slams into him, and man, he just takes off. We've got our answers there, and I think we're done. How about you? Did you get those okay? Well, we can also calculate the kinetic energies. Let's do that. Now, kinetic energies are not going to be conserved because some energy is lost in the collision. Temperature effects, mainly. But it'd be fun to get the initial kinetic energy, the total initial kinetic energy. I tell you what it'll be. It'll be 1/2 3 kilograms times 8 meters per second squared plus 1/2 2 kilograms times 4 meters per second squared. Help me get the initial kinetic energy. Here goes. Well, I might have done that right. I'm coming up with the initial kinetic energy is 112 joules. If that's not right, let me know. Now let's get the final kinetic energy. The final kinetic energy is going to be 1/2 3 times the 0.16 squared plus 1/2 2 times 8.24 squared. Do that and we'll get the final. Here goes. Well, I got the final, I think the final kinetic energy, if I did it right, and if I didn't, please let me know. I'm getting 67.936 joules. You know what? We lost some kinetic energy. We had 112 joules to start with, and now we only have 67 point something joules. Where'd it go? Mainly temperature effects. We do not have conservation of energy here, do we? Any questions on that? Okay, well, let's show you how you can measure this coefficient of restitution. I'm going to erase all this, and we're going to talk about measuring the coefficient of restitution. We have 12 minutes. We can do a lot in 12 minutes. Is there an E there in measuring? I don't think so. I think I did that right. But if I didn't, let me know. Measuring E, the coefficient of restitution. Now, how do you measure it? Well, if you take a, I don't know, a tennis ball maybe, here's a tennis ball, and let's drop it on the sidewalk, maybe 1 meter, okay? We're going to drop this tennis ball 1 meter. And you know what happens when that ball hits the ground there? It kind of flattens out on the bottom a little bit. The collision takes place very fast, but right in the very middle of the collision, the bottom of the tennis ball, it's kind of got a flat spot on it. And then the ball bounces back. There's restoration. See, the ball restores its original shape and it bounces back and it goes up here. But you know what? It doesn't make it quite, it doesn't quite make it to the original 1 meter. Now, I've got a tennis ball out in the garage. I should have gone and gotten it and we could have actually measured this. Do I have time? No, I don't. But you could do this at home. All you need is a ball. It doesn't have to be a tennis ball. It can be any kind of ball. And let's suppose it doesn't bounce back. You know it won't bounce back all the way. You know that it's not going to bounce. Let's suppose it bounces back 80 centimeters or 0.8 meters. We're going to find the coefficient of restitution of that tennis ball. I don't think the mass matters. It doesn't matter what the mass is of the tennis ball because the coefficient of the restitution is, it's the, now you got 2 bodies here you got to understand. Here's, we'll call body B is the tennis ball and body A is the sidewalk. Body A is the sidewalk. We're going to drop the tennis ball on the sidewalk. And so you got body B minus body A. Now these are the final, remember, in the numerator, you have the restitution values. And here's velocity of A, that's the tennis ball. This is the initial minus the initial, okay, I'm getting mixed up here. Yeah, this is the initial velocity of the sidewalk. Well, the initial velocity of the sidewalk is 0. It's not moving at all. And the final velocity of the sidewalk, wait a minute, now where's the sidewalk? No, I did it wrong, just a minute. I'll get this right in a minute. B minus A minus B. Yeah, here we go. Okay, I think that's the correct equation. Now, the final velocity of the sidewalk is 0. It's not moving. And you know what? The initial velocity of the sidewalk is 0. It's not moving. Now, if we can only figure the final velocity of the ball. Now, what they mean by final is right after the collision. And what they mean by, wait a minute. Now this has got to be initial. Yeah. What they mean by initial is right before the collision. See, right before the collision, the ball is right here. It's just getting ready to contact the sidewalk. And then it flattens out and you get this flat spot on the bottom at the maximum of the collision. And then the ball restores and it's just ready to take off. And see here, it's got a velocity going up. This is the velocity of the ball final. That's what I mean by the velocity of the ball final. It's right after the collision. And this is coming this way. This is the velocity of the ball initial, before the collision. Okay. We can get those. Let's get this first. What is the velocity of a ball that you drop from 1 meter? I don't know what the mass is, but it doesn't matter about the mass. If you drop a ball from 1 meter, isn't there an equation that says the distance equals 1/2 AT squared? Nah, we don't want that. Never mind, because we don't know the time. How about this one here? The final velocity minus the initial velocity, which is 0, equals 2 times acceleration times your distance. You guys remember that formula? Well, we can get this. Now, what this is going to be is the what I call the initial velocity of the ball just before the collision. See, here the velocity of the ball is 0. Here, the velocity of the ball just before collision. 2 times acceleration. Well, what's the acceleration? Well, it's 9.81, isn't it? 9.81 meters per second squared. Now, it's actually a negative if you're going up is plus, but see, this distance is negative. If up is plus, then the distance traveled would be delta y, which would be negative. So you have 2 negatives. What it amounts to is you got 2 times 9.81 times 1 equals the velocity of the ball squared. Okay, so what is the velocity of the ball? Go ahead, I'll wait for 30 seconds. What do you get? Hurry up, we only got 3 or 4 minutes. Did you get 4.429 meters a second?
Uh-huh.
Wonderful. Look, we just figured out this right here. Now we're going to figure out the final velocity of the ball. Now that's immediately after collision. We can use the same equation here. It's just that the delta y would be positive if up is plus. And so what you'd have is what we're after now is this, the velocity, the final velocity of the ball immediately after collision squared I got it backwards. The velocity up here is 0 when it stops, minus this velocity of the ball right after the collision squared is equal to 2 times 9.81 times 0.8 meters Now, wait a minute, I've got a little trouble with my minus sign here. Yeah, well, this is a minus 9.81 because it's going up, but gravity's, the 0.8's going up, but the gravity's going down. I think we're okay. Solve that and we'll get our velocity of the ball here. Here we go, right after the collision. It is did you get 3.962 meters a second?
Uh-huh.
Yay, wonderful. So what we have here is 3.962 meters per second minus 0, because that sidewalk doesn't move, divided by 0 minus, now here's where I'm running into this problem with the negatives. It's 4.429 meters a second coming in. But see, if up is plus, that's a minus 4.429. See, this is a plus. This thing takes off with 3.962, but this thing's coming in with a 4.429 meters a second, but it's going down, which would be negative. And so here we go, we'll get our coefficient of restitution. It is I got 0.89, 0.895. I see if it was a perfect collision, that coefficient would be 1. But it's not perfect. It's well, it's pretty close, 0.89. That's pretty darn good. But I've shown you how to measure the coefficient of restitution. All you need is a tennis ball and a sidewalk. Okay, guys, it's sad, but our time together has come to an end. Go work on your test and turn it in by whenever, what was it, Saturday? I think so. Have fun.
Yep.
Any last words? Because I'm going to click this red button here.
Thank you.
Thank you,
Where are we
guys.
supposed to find the test?
I will see you
Thanks.
when? Monday at 9:30.
I can't
Bye-bye,
find the
Yeah,
test.
everybody.
Yeah, where's the test at?
Yeah, your test is due Saturday night.
It's not on Blackboard that I see.
available.
It's not on Blackboard.
No.
It's not?
No, sir.
Well, I'll
it's
make
not.
sure it is. I'll talk to my IT person. It should be. I'll talk to my IT person. It should be available right now. I'll check on that.
Okay.
Okay, ta-ta, everybody.
Thank you.
Thank you.